Hello, welcome to this presentation, Kube5G, a cloud-native 5G service platform. My name is Osama Arouk and I'm from Eurocom, France. In this presentation, I will give firstly a general overview of Kube5G. Then I will present our new design of cloud-native functions and nested layer design. Kube5G operator for the objective of automating the service deployment and configuration will be presented. Finally, I introduce some results to benchmark cloud-native design and how much they are feasible for telco domain. I finally finish with some conclusion remarks. What is Kube5G? Kube5G is a realizable, agile service platform for supporting 4G, 5G cloud-native applications. It is a novel approach in building and packaging a cloud-native compliant telco network function in a form of nested, well-defined layers, as we will see later. Kubeflow also supports a workflow of continuous integration and development operations in support of multi-version network functions, say physical, virtual and cloud-native functions. And finally, a set of extensions to support additional functionalities in Kube5G, like Kubeflow for machine learning in a cloud-native environment. Our core contribution in this paper, Kube5G, is a novel cloud-native 5G design that is in line with the spirit of a cloud-native computing foundation, CNCF, and the needs of an agile, scalable, and on-demand service-oriented mobile network architecture. Kube5G architecture is composed of, from bottom to top, infrastructure and software-defined resources, and the infrastructure can ideally support any type of deployment, regardless whether it is bare metal, virtual machine, or any private public hybrid cloud. The container orchestration acts as both as infrastructure manager and as application manager. Thus, the container orchestration is responsible of controlling infrastructure resources like compute, storage, and networking. As infrastructure manager, the container orchestration has many responsibilities such as orchestrating the allocation, upgrading, releasing, or reclamation of resources, including resource optimization and managing the mapping of virtual physical resources. As application manager, the container orchestration is responsible of cloud-native function instantiation and reconfiguration, CNF, software update and or upgrade, downgrade whenever needed, and cloud-native function scaling. Kubernetes is a good example of such container orchestration. Kube5G supports the coexistence of both VNF, virtualized network function, and cloud-native network function as currently required for 4G and 5G network functions. For both VNF and CNF, a runtime execution is needed, where Docker is a good example for CNF runtime execution. Regarding the VNF is generally any virtual function not developed to be cloud-native compliant, which are generally monolithic functions or entities that are dependent on the environment and or hardware. In order to allow such functions to be executed in a cloud-native environment, for example Kubernetes, the runtime execution environment is needed, such as Virtlet and KubeVirt. Examples for CNF functions: open-air interface entities for the RAN and core network, FlexRAN, and LLMEC. Supporting APIs for cloud-native functions is very important for the communication between the services as well as remote interaction with them. Finally, the extensions play an important role in the Kube5G in order to support many value-added functionalities, such as monitoring and network intelligence like Kubeflow, cloud-native network deployment and automation via Kube5G operator, that is OpenShift operator, as we will see later. Our second contribution in this paper is the nested layer design of a cloud-native function, which is compliant with the 12-factor methodology. The layers are loosely coupled with each other to allow independent lifecycle management process to occur. Similar in spirit with Docker, the nested layer design allows the reusability across different layers. This is of paramount importance in a cloud environment to minimize application update, upgrade time to do CI/CD, retain service continuity when updating, upgrading the application by keeping the application data outside of the sandbox, and allow application portability across different execution environments. These layers are as follows. The first layer is the sandbox, which isolates the application from its runtime execution environment and grants access to only the resources that are required for proper operation of the application. Sandbox is thus similar with Android and iOS applications. It is a self-contained package where all applications dependencies are embedded, thus achieving application portability. Snap is a good example of sandbox. The sandbox contains the application by itself, its library and binary dependencies, and front-end as a value-added service such as versioning capabilities, monitoring and configuration APIs exposed by the application. The second layer is app data, which stores all the application-specific data required for the service elasticity, for example, or redeployment, scalability, etc. It also includes credentials, configurations, and runtime stats and logs stored across different apps revisions. Such decouplings makes the application stateless and thus significantly improves the efficiency of lifecycle management process. The next layer is utils and hooks, where the utils are a set of helper tools that are needed inside the container to perform runtime testing or monitoring of the application, while hooks are in charge of application lifecycle management inside the container, such as application starting, restarting, reconfiguration, or sandbox upgrading. The last layer is the container, which is a software package containing everything required to run the application properly. Different from sandbox, container contains system tools, libraries, and settings, thus making the software completely independent of the environment of execution. One of the main important features of the container is its elasticity, where many instances of the same application can be run on the same host or being distributed over many environments. The container supports two types of ports according to the 12-factor methodology. The first one is binding port to connect to external applications as service producer or consumer for the purpose of, for example, logging and monitoring like Flask and OpenAPI. The second port is meshing services to connect to the external applications and share states for a proper operation of embedded applications, for example, database. This port is also used to store the app data outside of the container when needed, for example, when a container needs upgrade or in case of failover. Before introducing Kube5G operator, let's give a general overview on how Kubernetes works. Kubernetes runs and manages containerized applications according to the specification, say service specification. This is done by continuously checking the cluster to ensure that the ideal described states of the service is with the right number of instances on the right infrastructure with the right deployment, rollback, and failover strategies. In this example, we see that Kubernetes detects that the actual state is not equal to the ideal state. In this case, Kubernetes will take the right action to make sure that always the actual state is equal to the ideal state. So, Kubernetes ensures always that the ideal state is equal to the actual state, where it can automate most of these tasks for stateless applications. However, Kubernetes cannot do such automation for stateful applications, in addition to many other functionalities that cannot be done directly via Kubernetes, like metrics alerts, log processing and workload analysis, auto reconfiguration and abnormal detection, or generally autopilot. However, this can be done easily via the operator. The operator is a scalable, custom version of Kubernetes control loop for stateful applications. It determines whether your application is running correctly according to the instructions. With the help of custom resource definition, the users can interact with the operator and the service through these objects. Note that the CRD exposes only the options that make sense to be exposed to the user. An operator can also set a new state to your service. If this is the case, the operator will take this new update and will push it to your service to make sure that always your service is up to date and equal to the new ideal state. Due to all the aforementioned reasons, we propose Kube5G operator, which is built using OpenShift operator SDK. Kube5G operator can automate for G5G services with the installation, configuration, updates, upgrade, and management in a cloud-native environment. Regarding OpenShift operator, there are three main ways to realize it, each with its capabilities, as shown in this figure. In order to get default capabilities of an operator for 4G and 5G services, we developed Kube5G operator in Go. To show the efficiency of Kube5G as well as benchmark it against different deployments, we assess experiments with the following network setup as shown in the figure. Private cloud that is composed of two powerful workstations with Ubuntu 18 and a third workstation as Kubernetes master for the Kubernetes deployment. The remote radio head of RAN is composed of USRB, duplexer and antenna operating in FDDC zone mode with band 7 and 5 MHz as channel bandwidth. iPhone SE is used as user equipment, where the considered network is 4G plus with support of disaggregated RAN, that is function split, and in particularly the function split for F1 interface. And in this setup, we used OpenAir interface and Mosaic 5G platforms to realize the experimentation. Here we show the detailed setup for the considered deployments. For bare metal deployment, we use one workstation that is equipped with USRB, duplexer and antenna. The second deployment is Docker Compose, where the setup is similar to that one for bare metal. The last deployment is for Kubernetes, where we use two workstations as Kubernetes workers, and one of them is connected to the USRB to serve as remote radio head for the RAN part of the network. Regarding the results in terms of deployment and reconfiguration time, we use the following metrics. The download time is the time to download network entities from the store, which is Snapcraft for snaps and Docker Hub for Docker images. The service provision time is the time to bring up the network service until the users start consuming the service, where this time is composed of configuration and deployment time. Reconfiguration time is the time to reconfigure one or more entities and bring the service up again. That is, the users are connected and start consuming the service. From this figure, it's clear that the download time for the snaps is much smaller compared to the Docker and Kube5G operator. This is because the footprint of snaps is much smaller compared to Docker and Kubernetes, which are 528 MB for core network and 745 MB for RAN Docker images, while it is only 58 MB for core network and 247 MB for the RAN snaps. On the other hand, the service provision time for the snaps is much higher since the configuration is done manually, while it is not the case for Docker and Kube5G operator. The service provision time for Kube5G operator is a little higher than that for Dockers, as there is additional time to bring the Kube5G operator up before provision the network. In case of reconfiguration, we can see that the Kube5G operator outperforms both Docker and snaps, since the configuration is done automatically and only the concerned entities will be restarted, while the whole network shall be restarted for Docker and snaps. Therefore, Kube5G operator brings significantly improvement for the network in terms of the deployment and configuration and reconfiguration. Regarding the TCP/UDP traffic, where we used IPv3 for that, we can see that all types of deployment have similar performances. Therefore, with Kube5G operator, we gain a lot of improvement in terms of auto deployment and configuration without degrading the service quality. Finally, we show here the global performance for these three types of deployment, which is collected using mperf. Again, all the deployments have similar performances regarding all the metrics: downlink, uplink rates, latency, browsing and streaming traffic performances. In this paper, we proposed a novel cloud-native function design as a nested reusable layers to ease building, packaging, and upgrading of multi-version network functions during CI/CD process. We also presented a concrete implementation of 4G, 5G cloud-native functions with automated lifecycle management operations using Kube5G operator. Kube5G is benchmarked against bare metal, that is Snap, and Docker deployments, demonstrating its feasibility and efficiency for fast rollout of 4G 5G network services, where 4G 5G network can be provisioned in less than 2 minutes and can be updated, reconfigured as part of autopilot feature of Kube5G operator in less than a minute. As the feature works, we plan to extend the features of Kube5G operator for monitoring, analysis, and auto-config tuning, and also to support artificial intelligence and machine learning in Kube5G using Kubeflow.